Hi everyone, my name is Zhenling Huang, and today I want to share my supervised deep learning project to predict Airbnb pricing to you. Our goal is to predict what a reasonable nightly Airbnb price should be based on its listing information. By decoding how these features drive prices in various models, we can help guest budgets smarter and encourage hosts and platforms to be more transparent. We source raw data from inside Airbnb, which provides daily updates of listings, calendar, and review files for cities worldwide. Because each city reports prices in local currency, we tag ISO codes and apply European Central Bank exchange rates to convert each prices into USD. Plot New York and London price maps reveal a distance decay pattern, highest rate near the center, declining with distance. We quantify this by computing each listing distances to the city centroid and adding it as a feature. Textual tone can carry pricing signals. Think cozy can now view apartment versus budget studios. We ran each title and description through sentiment analysis, extracting negative, neutral, positive, and compound scores. To maximize data use, we then filter to only the predictors our model required and impute any remaining missing value of zeros. That left us with 98.8% of the original dataset. Finally, we apply the random 60-20-20 split for training, validation, and testing purposes. Here we benchmarked a random forest regressor as a strong baseline model. A forest is simply a sample of n decision trees. Each tree is grown up to a maximum depth of d, splitting when at least S sample remains, and requiring at least L samples per leaf to prevent overfitting. At each split, we randomly select F features to inject diversity across trees. After each tree predicts, we average all predictions for the final output y. Using random search CV, the best hyperparameters was including 300 individual trees and the maximum tree depth of 64, minimum sample split of 2, and minimum sample leaf of 1, and selecting base 2 logarithm features which balance per tree complexity with ensemble variance reduction. On our test set, tuning reduced root mean square error from $1,045 to $1,037, raised R squared from 14.8% to 16.1%. Our first deep learning model uses Kira's Sequential API, which defines neural networks as a straightforward stack of layers. This linear format makes it easy to prototype feed-forward architectures by listing each block in sequence. To guard against overfitting, we apply dropout after each hidden layer, randomly zeroing out a fixed fraction of neuron activations each batch so no single unit dominates. Use Bayesian optimization, we systematically explore the layer sizes, dropout rates, and learning rates. The search converged on a 3-layer configuration. The first hidden layer contains 256 neurons with 30% dropout rate, the second with 96 neurons and a 20% dropout rate, the third uses 48 neurons with 40% dropout, and an initial learning rate of 1.84 times 10 to the negative 4. In testing, this tuned sequential model achieved a root mean square error of $889, improving on the untuned $898, and explained 61.9% of the variance compared to the untuned 57.5%. To better capture the differing nature of our inputs, we turned to Kira's functional API to build dual branch model before merging their outputs. This dual branch design processes amenity categorical flags and continuous numeric predictions in isolation, each through its own series of dense ReLU activation dropout layers, so that each branch can learn specialized representations. In 20 max trials with epochs equals 50, batch size equals 64, and patience equals 10, Bayesian optimization tuned the amenity branch and numeric branch with various numbers of neutrons and dropout rates. After concatenation, a 32-unit dense layer with 0 dropout feeds into the final linear outputs, and the initial learning rate was tuned. From the graph, the untuned model on the left can observe a small train validation gap, indicating mild overfitting. After Bayesian tuning, the loss dips below 0.17 within 5 epochs, and the training and validation curve nearly coincide, evidence of effective regularization and excellent generalization. On our dataset, the tuned functional model achieves root mean square error of $874 and the R square of 63.9%, outperforming both sequential API and the random forest baseline. This confirmed the branch-specific architecture combined with systematic hyperparameter search yield the strongest predictive performance on our Airbnb project. Further improvements are still possible. We utilize a richer feature engineering, adding interaction terms of key predictors and tune batch sizes as a parameter to enhance accuracy.